So, welcome everyone to today's TCS seminar. We have Clément Legrand-Duchesne from this university. Clément did his PhD in Bordeaux and then he came for 2 years. He's already for almost 2 years in our group, and he will speak about Dirac's theorem and the switch geometry of perfect matchings.
Thanks for the introduction and thanks for coming. Everything I'm presenting today is joint work with Ross Kang. And also let me mention before I start, I'm also very happy to answer questions on the fly. So if you have anything that bugs you, just interrupt me. So let's talk about Dirac's theorem then. So the question, like a standard question in extremal graph theory, is we have some specific structure and we're asking like how many edges, for example, or like what is the minimum degree or what is the maximal density of a graph that does not contain this structure. Okay, so for Dirac theorem and Dirac type problems, the question is we have some spanning structure H on n vertices, and we're asking what is the minimum degree of G such that G does not contain H inside. Okay, so here when I'm saying contain, it's not as an induced subgraph, of course, because this would not make much sense. So it's just as a subgraph. And then there's so the easiest example of such statement is for perfect matchings and Hamiltonian cycles. And so the theorem of Dirac from 1951 says that if you take a graph and it has n vertices and minimum degree at least n over 2, then it contains a perfect matching and a Hamiltonian cycle for sure. Okay, so the minimum degree you can have without this perfect matching is less than n over 2. And how do we prove this thing? Well, it's so this is tight. Sorry, yeah. So this is tight. You can see this by taking like bipartite graphs with the two sides that are slightly unbalanced. This is like just below n over 2. Or you can also take two cliques. This is also just below n over 2, and you don't have perfect matchings because of parity reasons. You also don't contain Hamiltonian cycles in those examples. So this is tight, and how do you prove this theorem? It's actually very simple. We use something called the switching method. And so what we're trying to do here is to construct our matching greedy. Okay, so you take your graph, take some maximal matching inside of it. And so because it's a maximal matching, I cannot extend it, and whatever is left is an independent set. Okay? And so now what I will try to do is modify this matching a bit to extend it by adding some vertices from this big independent set that is left here. So the vertices here, well, the thing is it's an independent set, so all the neighbors are on the other side. Okay? So they have at least n over 2 neighbors on the other side. Okay? So given some vertex u, let me denote y, the set where it's all the vertices y that are matched in my matching to some neighbor of u. Okay? So this set y, it has size at least n over 2. And then when I take any other vertex, in my leftover here on the right, well, it also has n over 2 neighbors here. So the neighborhood of this guy and this set y must intersect. And because they intersect, then I have this small thing that I can find somewhere. This is just by pigeonhole. And thus, well, if I replace this edge by those two edges, I have now a matching that's bigger. And I can continue like this, extending my matching on and on. Okay? So this way, I can construct a matching of size n, so with n over 2 edges, and I'm happy. Another way of proving this theorem is actually doing similar tricks with Poisson rotations to extend some path until you have a Hamiltonian cycle. And once you have a Hamiltonian cycles, if your number of vertices is even, you can take one edge out of 2 on this cycle, and you also get a perfect matching. This proof is kind of specific to perfect matching, so we like it. Okay. So that's the proof of the Dirac theorem. And more generally, we say that a graph is c-Dirac if its minimum degree is at least Cn. Okay, and most of what I will say today holds in other settings. Okay, so for example, if you're not interested in perfect matchings of normal graphs, but of balanced bipartite graphs, so you have two parts, a bipartite graph with both big independent sets that are of size n, okay, and the minimum degree is Cn, well, the same thing holds. Also, if you're trying to find some matching that is not a perfect matching, but a fraction, like only gamma n edges for some gamma, if you just multiply the constant here, you will get the same result. Okay, so what I'm saying here is just that up to multiplying by some constant, which is the natural constant you would think of in this situation, everything holds for partial matchings and for balanced bipartite graphs as well. So I will only focus on general graphs, but you can generalize this result. Okay, so here what we've said with this Dirac theorem is that below n/2 you're not sure you have a perfect matching. After n/2 you're sure you have a perfect matching. And in fact, this n/2 barrier here, it's a threshold, and there's like a sort of phase transition happening. So this is called supersaturation. And basically what's happening is that above this threshold of n/2, the amount of perfect matchings you have becomes enormous all of a sudden. So you go from having potentially 0 perfect matchings to having a huge amount of them. And when I'm saying huge amount of them, it's something like minimum degree over e to the power n/2. So this is huge. So that's a transition, phase transition in terms of number of perfect matchings. But you can also say something about how those matchings are distributed in the graph. Okay, so there's this result from 2 years ago where they built some sort of distribution on perfect matchings in a c-Dirac graph. And you don't really have to know exactly what properties this distribution verify. But basically what it says is that the perfect matchings are sort of everywhere in your graph. Okay? They're very well spread within your graph. And one consequence of this is that if you take a 1/2 Dirac graph, it contains a perfect matching in a very robust sense. Okay, so before I talk about c-Dirac graph, let me talk about a clique. If you take a clique and you sample the edges with probability log n over n, you will still contain a perfect matching. Okay, so this is basically the same thing as saying that g n big O of log n over n contains a perfect matching with high probability. And so here we started with a clique, but you could say, okay, instead of starting with a clique, why not start with a graph that contains loads of perfect matching, like a c-Dirac graph? And that's exactly what they do here. So if you start with a 1/2 Dirac graph, it has lots of perfect matching, and if you sample the edges with probability big O of log n over n, you still contain a perfect matching with high probability. Okay? So this tells you that to kill all the perfect matchings, it's hard to do it at random, and those perfect matchings are everywhere. They're very well spread in your graph. Okay? So that's the intuition. So basically, what have we said so far? Below n/2, maybe no perfect matchings. After n/2, lots of perfect matchings and kind of everywhere. And here, this kind of like makes us think that something else should happen here in terms of phase transition. We think that the space of perfect matching should have some nice geometrical properties when the minimum degree goes above n/2. So that's what started this work, and that's the question we're trying to answer today. So the argument here is that because there's so many perfect matchings and they're kind of everywhere, they should start becoming close to one another, and they should form some sort of connected space with some metric that is natural. So let me give you a bit of more information of what I mean on this. And before I go explicitly on this, this type of question is actually super common in other fields. So if you're looking at random constraint satisfaction problems, basically the one like standard setup is, for example, you have a formula. It's a random formula, so you're taking clauses at random, and you're wondering what is the amount of clauses I can have on n variables before my formula becomes unsatisfiable with high probability. Okay. And so this is a threshold for satisfiability, but then you can look at the space of all truth assignments of your formula and go from one truth assignment to another by changing the value of just one variable. Okay, so this is a natural metric on the space of truth assignment of a given formula. Just changing one variable at a time, and this way you can sort of navigate in your space of truth assignment. And the questions they have is, well, what is the density of clauses you can have before this thing becomes connected or has like other kind of properties. Okay. So typically, what they obtain is something like this. When the constraint density is super high, well, we simply have no truth assignment for our formula. There's no solution. Okay? And on the contrary, when our density is sufficiently low, you have like loads of truth assignment, and therefore some sort of super well connected space with this metric. And then in the middle, there's a different series of thresholds that this density goes through. So at some point, you stop being connected with high probability, but maybe you still have some giant component, like a component containing a linear fraction of your space. So that's this threshold here, and then at some point you don't contain for sure giant components, so you have like smaller components here. Then the clustering threshold is the threshold at which you start having some exponential number of clusters. Okay, so connected components. Yes.
Connected in the reconfiguration work when you just switch one variable.
Yes. Yeah. So think about this formula. You switch your variables one at a time. Okay, so you can think of this as a reconfiguration graph, but also you could think of this as just simply the space of all formulas with this metric, which is the Hamming distance, and this gives you edges. And so you're interested in like the connected properties of this thing. So the number of connected components at some point becomes super large, and that's the clustering threshold. It goes from being sub-exponential to exponential. And then there's other thresholds. So for example, the thawing threshold, also called sometimes freezing threshold, is a bit different. Here you're wondering, if I look inside one cluster, can all the variables change within this cluster, or is there a variable that will be constant through the cluster? Okay, so if this variable is constant through the cluster, we say that it's frozen. And so this freezing or thawing threshold is when you have a linear number of variables that become frozen within all clusters. Okay. So those are the different thresholds we're interested in. Typically, the properties of our space of truth assignments of our formula. These are the typical questions we're interested in, determining those different thresholds. And so typically, those thresholds happen very close to one another, and those are also quite close to one another. Okay. So tell me if I'm saying something wrong, because you're the expert in the room about all this stuff. Okay, so this has been done a lot for like random things, but this has not been studied very much for like deterministic problems, extremal problems like Dirac problem. Okay, so what we're trying to have today is a similar picture, but for perfect matchings of a c-Dirac graph. The question is, what is the c at which you have those different thresholds? Yeah, so what I'm wondering if you're doing reconfiguration, so if you're drawing, RCSPs, thawing is sometimes called freezing, and in reconfiguration, what we call freezing is usually the isolated vertices in our space, the isolated points. So here it's not the same thing. So. Okay. Do you have any questions on this sort of diagram of what we're trying to do? No? Okay, so first thing we need to do is to define some natural metric on our space of perfect matchings. So you have two matchings, and we've seen that for truth assignment, for example, we're taking Hamming distance. So this is like the most natural metric you could think of. Let's do the same thing here. Okay, so two matchings, if you compare them, the symmetric difference cannot be just on one edge, right? Because if you remove this edge, you have to add it back directly. So you need to remove several edges. So if you remove two edges and you replace them by some other thing, then like this, I have those two edges. Those are blue in my matching, blue matching, sorry. And I replace them by those two edges. Then my symmetric difference is 2. And so what we will call a k-switch is exactly this operation, removing at most k edges and adding back at most k edges. I mean, the same number. So we see that k has to be at least 2. Okay, so I will denote hk, the reconfiguration graph on perfect matchings of G under k-switches. Okay, so basically, in this reconfiguration graph, my vertices are my perfect matching of my original graph G, and I have an edge between two perfect matchings if they differ by a k-switch. So if I can go from one to the other by removing at most k edges and adding back at most k edges. Okay, so this is the graph whose geometry I'm investigating. And so the results we have is we obtain different bounds on the different thresholds. So let's first look at the picture of what's happening when k is at least 3. Okay, so think about 3 switches, removing 3 edges, adding back 3 edges. Maybe the most interesting one is the connectedness threshold. So we show that the graph becomes connected for sure when the minimum degree is n/2 plus 2. And we have example with n/2 where it's not connected. Okay, so the threshold is somewhere in this narrow window. And actually, as soon as it gets connected, the graph we have becomes also an expander. So like it has like very strong expansion properties, and random walks on them mix in polynomial time. That's what we get for connectedness and expansion. Then for giant components, we have some lower bound of n/2 minus some constant. So it's also some small window. This constant depends on the size of the switches you're doing. So yeah. And then for thawing and clustering, it's n/2 minus something that is negligible in compared to n. Okay, so everything is happening very close to n/2. We go from having some space of perfect matching that is possibly containing like an exponential number of connected components to having something that is super strongly connected. Okay, so that's the picture for 3 switches, and actually for 4 switches we get something similar up to some constant. Okay. So one thing I haven't talked about yet is isolated matchings. So the surprise we had was that isolated matchings, in fact, can appear sooner. Okay, so we have this bound. So we show that you have no isolated matchings. You have no isolated matchings if your minimum degree is larger than this thing. Okay, but you can have maybe isolated matchings. So it's not really n/2 here. We have some kind of different behavior. And this bound here is related to the Caccetta-Häggkvist conjecture. So we'll talk about this in a bit more details later. Okay, so here we've seen what happened for k equal to 3 and larger case. But we haven't thought about 2 switches, which is like the most natural operation you could think of. And for 2 switches, we have some sort of weird things that are going on, some sort of artifacts happening. And in fact, the connectedness threshold is around 2n/3 instead of n/4 and n/2. Okay. And then the bounds we get here, the lower bounds are still valid, but we cannot make them better. So this giant component and this Stoic clustering, they're happening somewhere here. And for isolated matching, we have a much more precise answer. Yes?
Just to be sure that I read correctly. So for example, the second line says that there exists a constant that if you have strictly less than n half minus this constant minimum degree, then you have no giant component, or is something else that you show?
Yes, so what we show is that for any, okay, so giant component, it's something that is parameterized, right? So we show that for any constant, lambda, there exists a constant, small c, such that if your minimum degree is less than n/2 minus c, then you don't have a connected component of size lambda n. Okay, so this bigger of one depends on the constant you're choosing, but yeah. Okay, so that's something slightly annoying to formalize, so you can think of it by taking some arbitrary constant. Yes.
So then why does the upper bound not depend on the constant?
Because here you become connected with n/2 plus 2, so you will have a giant component for whatever thing you have.
So for small lambda, you can have several giant components, right?
Yes. Yes. And in fact, the examples we're building have components of equal size, so this is typically what's happening. Okay.
And are these intervals tight in the sense that if you are within the interval, then there are examples showing?
We don't know. We don't know. So we have like constructions below this, proofs above this, and in the middle we don't know. So most of those intervals are tight in the sense that there's a very small gap here. But for example, for this one, we don't know what is if we have a giant component anywhere between n/2 and 2n/3. So that's still an open question. Yes.
But it is possible that you have some values for which there exist graphs, which, I don't know, you would have this giant component, and there exist other graphs where you would not have those giant components, and this is...
Yes, but that's actually, so when we say a lower bound, we're not saying that every graph has no giant component. We say that there exists a graph with no giant component. Okay, so let's start with connectedness. And for simplicity, instead of doing 3 switches directly, let's look at 4 switches because it's much simpler. Okay, so we're trying to prove that given any 2 matchings, I can go from my matching that will be red to my matching blue with operations by removing 4 edges and adding 4 edges at every step. Okay, so that's what I'm trying to achieve. And here the minimum degree is at least n/2 plus 1. So those are my 2 matchings, M and N. They're in blue and red. And so here my measure of the progress I'm making is the size of the symmetric difference between M and S, the number of edges that are not the same. And so what I'm trying to do is to reduce this thing at every step. So if I look at the symmetric difference, very observation, it's a collection of alternating paths on blue and red. Okay, so if one of those alternating paths has size less than 4, then I can remove the blue edges, add back the red edges, and I made some progress. Okay, so I can assume that this thing happens nowhere in my graph, and that all my alternating paths are long alternating paths. Okay. So, as I said, if it's possible, if I have an edge here or an edge here, then by removing blue, blue, and adding red, red, I will reduce my symmetric difference. So I can assume that those 2 edges are not here, and similarly, the edge between U3 and U6 is not here. Okay. So now I will do something that is actually similar to the proof we've done for proving the existence of perfect matching at the very beginning. So let V prime be all the vertices but those 6 vertices here. Okay? Let Y be all the vertices in V prime that are matched to a neighbor of U6. Okay? So because U6 is not adjacent to U1 and it's not adjacent to U3, it might be adjacent to U2, U4, U5. So that means that the size of this Y is the degree of U6 minus 3. It's at least this. So it's n over 2 minus 2. And now, well, the degree of U1 is also n over 2 minus 2. So by pigeonhole, this Y and the neighborhood of U1 intersected with V prime must intersect. So that means that I can find an edge here, and now I have this. And here I'm super happy because I can now remove those blue edges in this small 8 cycle, replace them by the red edges, and I made some progress. The number of common edges here, maybe this was blue and red, so maybe I've lost one, but I've gained 2 of them, so I made some progress. Okay, so I keep doing this over and over again, and this way I reach m from n in a linear number of steps. Okay, so we've just proven connectedness. Okay, so I told you that connectedness, when you had connectedness, you had expansion directly. So at n over 2 plus this constant, you also get expansion for free, basically. And so let me give some more details on what I mean by expansion. So so a graph is an expander. Okay, if there is no way of cutting it with a few number of edges compared to the size of the 2 sides of my cuts. Okay, so that's one way of looking at the cut, is with this Jagiellonian constant. Another way of thinking about expansion is to think about random walks. Okay, so this equivalence here, it's not a complete super clean equivalence, because when you're going from one side to the other, you sometimes take a log n factor. Okay, so but basically expanders are graphs on which random walks are efficient. Okay, they converge to uniform distribution in polynomial time. And so what we're trying to do here is to do some random walk on our graph H, and to bound the amount of steps we need to do before we come epsilon close to uniform distribution on my graph. To do this, there exist several methods. So one of them is by doing some couplings argument. One of them is the canonical path method, and we can also use some spectral method. So today we'll be focusing on this canonical path method. And my goal is not to give you the full proof, but rather to give you like some small ingredients, and also to give you some like rule of thumbs to decide when you should use this method and when it has good chances of working. Okay, so what is the canonical path method? Basically, for every pair of matching, so here they're called x and y, because they're in my graph, but if you're just doing some random walk on some arbitrary graph, x and y are just vertices of my graph. Okay, so you take 2 vertices of the graph on which you're doing this random walk, and for any 2 such vertices, you define some path, and you say, well, this is my canonical path. Okay, so I have my graph, and for every x, y, I have this canonical path. And what I told you before is that my graph was not an expander if I had a way of cutting it with few edges with the 2 sides that were big. Okay, so typically, if this happens, whenever I would take x and y on different sides, I will have lots of canonical paths that are going through this middle thing. And that's the thing I'm trying to avoid. Okay, so the canonical path method consists in defining those paths and showing that it doesn't have any congestion. So for every edge, there's a few number of paths that goes through this edge. And if you're able to show this, then you will get some bound on the mixing time and in turn on your expansion. Okay? So it's all about finding a collection of paths that are very well spread in your graph and that do not use one single vertex or one single edge a lot of time. And so typically, when you're doing some reconfiguration proof where you're reducing your symmetric difference one step at a time and you're able to choose where in your symmetric difference you're doing your operation, then this thing will work very well. Okay? And so here, what we do is we just open the proof we had for connectivity, and then we count the number of paths that are going through one transition, and we show that this is polynomially bounded, and this gives us a bound on the mixing time. That's kind of the so it's just like basically we have this thing for free. We're just like doing some careful analysis, but the proof is really the same thing. So why do we care about expansion? So you could think about this as a structural property of your graph, but you might also be interested in actually doing random sampling of your perfect matchings. And then a classical approach is just to start anywhere in your reconfiguration graph, do random walk for sufficiently long time until you are close enough to some uniform distribution, and that's the perfect matching you output. Okay? So that's why we're interested in mixing times. We're interested in the efficiency of such algorithms, and this is governed by the mixing time. So what we've just proven was that the random walk in H4 mixes in time big O of n squared log n, where n is the size of my original graph, if the minimum degree of this graph was n over 2 plus 1. Okay. So we have some efficient way of sampling matchings. Yes?
But this mixing gives you just approximately uniform distribution, so there should be some approximation
yes.
factor in the time complexity, right?
Indeed. So, but the approximation factor always has the same form. So basically, this big O here, the constant in front depends on the epsilon approximation you want to have.
Okay.
But if you switch it, if you change it, it will just multiply by a constant, this whole thing. So if you decide in advance, I'm interested in like 1/4 approximation, then for all n you will have the same bound here.
But the dependence on this approximation factor can be huge.
So usually it's like it's log 1 over epsilon. Yeah. It's not that big. Okay. So unfortunately, this was known before. So in the 90s, Broder came up with a Markov chain on perfect and near perfect matching. So he was interested in sampling perfect matchings. And his idea was, well, navigating the space of perfect matching is sometimes not very practical. So instead, let's navigate in the space of perfect and near perfect matching. So near perfect matching is a perfect matching minus one edge. Okay, so I have at most 2 vertices that are not matched. Okay, and so he has some operation that sometimes goes from having a perfect matching to some near perfect matching, then maybe moving a bit in near perfect matching, going back up. And so he's just moving in this bigger space. And he proves that, well, the mixing time he gets is n to the 5 log n. So here you might say, oh, but that's not good enough, because then what we get is either perfect matching or near perfect matching. We're not completely happy. We're wanting to sample perfect matchings only. But the thing is that if your minimum degree is large like this, the ratio of near perfect matching to perfect matching is polynomial. It's of order n squared. So what you can do is perform your random walk for this time, n to the 5 log n, And because this ratio is n squared, if you do this n squared times, you will, with high probability, meet some perfect matching on the way. And therefore, you get some approximate sampler in time n to the 7 log n, which beats us by a factor of n. Okay? And actually, what we did here, it's not really novel in the sense that the canonical path method was introduced to handle this kind of stuff. Okay, so this is one of the textbook example of how you use canonical path method. It's on matchings with this broader algorithm. So here you might also wonder, well, why are we talking about Broder's Markov chain and not Jerome and Sinclair? Because it initially had some mistake and then they patched it later on. And so one motivation of Broder was actually not doing this perfect sampling, but doing some approximate counting. He was interested in the problem of computing the number of perfect matchings of a graph. So this is counting. This is some sharp P hard problem. But if you're only interested in approximate counting, then the complexity is the same as doing approximate sampling. So his original motivation was to do approximate counting. And in particular, if you look at perfect matchings of balanced bipartite graph, they count something called the permanent of some matrix, and this was studied also for a lot of time. So these were like the original motivations. And so they got this polynomial approximate sampler, and then I think it's an H here, but I'm not completely sure. They just got some perfect sampler in bipartite regular graphs. So this is the picture for expansion and mixing time. Okay. I will close the parenthesis on mixing time. And now you might think, well, you told us about 3 switches, and we've done 4 switches so far. So what happens for 3 switches? Well, it's actually super simple. Take 2 matchings, 2 perfect matchings that differ on at most 4 edges by a full switch. What we show is actually they differ by a sequence of 3 switches. So if H4 is connected, because every transition in this H4 can be realized by a short sequence of 3 switches, that means that H3 is connected as well. Okay? And how do we do this? Well, suppose you're able to find this configuration in your graph. So this is the cycle on which my 2 matchings differ. And what I will do is first do a 2 switch in this phase here. I get this. Then one in this one, and then one in this one. And I get something where everyone agrees. Okay, yes?
4 switch is not necessarily a single cycle, right?
Yes, it could be also two switches. But then, in particular, those are also 3 switches, so you're happy in this case.
So this is the only one that you do.
Yes. Okay, so then it's all about finding this configuration. So basically what we need is to find some edge in my matching with adjacency like this cyclically. And to do this, we do some short discharging proof. It's like half a page and just counting arguments. Okay, so this give, yep.
Why you cannot see it just be a path?
Because it's so if you take the symmetric difference of 2 matchings, because they are perfect, it's an alternating cycle, right? Every okay, so this tells us that this graph is connected. It is H3 is connected, and we have the lower bound as well of n over 2 minus 1. Just because if you take this graph here, so it has 4 parts of equal size, okay, bipartite complete graphs between them, and then those things are independent set, but those things on the side are cliques. So the minimum degree of this thing is n over 2 minus 1. And here, if you have some edge on this side in your matching, well, if you do a switch that involves this edge, it will not change the number of edges of your matching that belongs to this thing. And this is basically because you're not able to reach the other part of your graph here. So it will have to stay here, and this is why it doesn't change the number of edges within this. So this is an invariant, and we get a number of different connected components because of this. Okay. So to get from 3 switches to 2 switches, we do the exact same thing. We take some alternating cycle of length 6, sorry, and then we're trying to find this configuration inside, and if we have it, we're happy because we can simulate some 3 switch with a sequence of 2 switches. The problem is that to find this configuration, we need that the minimum degree is at least this quantity, so 2/3. And there's a good reason for that, because if we take the same example as what we had before, but with 3 parts, the same arguments give us that with this number of neighbors, you can have a disconnected graph. So when k is equal to 2, the connectedness and expansion things are happening at around 2/3 rather than n/2. Okay. What about the other lower bounds? So we talked about giant components, thawing, clustering, and this kind of stuff. So we have one general construction to handle all those things, and we just vary some parameter to get the different bounds we're interested in. So the lower bound, the construction looks like this. You have 2 big parts of equal size, and then you have a small set in which you have some cycles of length 2k plus 1. And then this set of cycles, you make it completely adjacent to one of the 2 sides. So here, the key observation is that, well, because if you look at a perfect matching of this thing, you will never be able to have edges inside here. Because if you have some edge here, then some guy on this side is not matched. Okay, because those 2 things are of equal size. So all the edges in my matching are in here and within here. And those are cycles of length 2k plus 1. So because they are cycles, there's 2 possibilities for each cycle. Okay, you can have either this or this. Okay. And because they are of size 2k plus 1, well, with a k switch, I cannot go from one position of my cycle to the other. So this thing is actually frozen. I cannot do any change here to modify those. Okay. So here, all this part is frozen, and the number of connected components is 2 to the power the number of cycles I had on this side. So those are my properties. I have this many frozen edges and this many components of equal size inside. And so by adjusting the value of p, if you take p to be constant, then you get the giant complement threshold. If you take p to be linear, then you get the clustering and thawing threshold. And if you take p to be just 1, then you get a lower bound connectedness. Okay. Okay, so this is for all the different thresholds where things happen nicely, let's say. And then there's this isolated matchings. And as I said, for isolated matchings, we're kind of surprised of what happened and what the threshold was. And so here we actually have some interesting connection with Caccetta-Häggkvist conjecture. So here, just for simplicity, let me talk about balanced bipartite graph here instead of regular graph of normal graphs, just because it makes the equivalence a bit nicer. But then I will very shortly discuss general graphs. So the conjecture of Caccetta-Häggkvist asks what is the minimum out degree that a graph needs to have before it has some directed cycle of length at most k. Okay, so I'm taking some oriented graph and I want a cycle of length at most k. What is the maximum out degree I can have before this happens? And so what they conjectured is that if my minimum out degree is n over k, then I contain a cycle of length at most k. And then there's this weakening of this Caccetta-Häggkvist conjecture where you replace out degree by semi-degree. So semi-degree is the minimum of out and in degree. And that's the same thing. And it's also open, and they think it's the same bound. And so this version with the minimum semi-degree, it's a mix of this Caccetta-Häggkvist conjecture and some other conjecture about regular graphs. So this is a very famous conjecture in extremal graph theory. And what we show is that actually the threshold for having no isolated matching is like in correspondence with the Caccetta-Häggkvist threshold. So how do we do this? Oh, sorry. Okay, so how do we do this? We have some sort of equivalence. So let's start with a graph of an oriented graph that has no directed cycle of length k plus 1. Okay. So whenever I have an edge between two vertices, sorry, I have this graph on n vertices, and the balanced bipartite graph I'm constructing has two n vertices. It's ai, bi, so for every I have ai in one part and bi in the other. And then my matching is just the edges ai, bi everywhere. Okay, so this is the matching I have. I want to show that it's isolated in my space of perfect matchings. And so the graph I'm starting with, whenever it has an edge between ui and uj, I add an edge between ai and bj. So when I do this, I get some bipartite graph, right? And now I know that in my graph that I constructed, what would a case which look like? It would look like this. I would have some edges, and because it's bipartite, this one is linked to this one is linked to this one is linked like this. This is what a case which look like in this balanced bipartite graph. And so here, in the original graph, this would correspond to some directed cycle of length k plus 1. Okay, sorry, so here we're taking a graph with no directed cycle of length k plus 1. Okay. So because it has no directed cycle of length at most k, well, I don't have any switches that are possible in my perfect matching, so it's an isolated matching. And you can do the same construction in the other direction. It works the same way, and you prove that you get the other direction. And so here the minimum degree relates, because here the degree of ui, the out degree of ui is the degree of ai minus 1, and the in degree is the degree of bi minus 1. So this is why the degrees relate, and we have this correspondence. So for one corollary of this is that for Caccetta-Häggkvist conjecture, we have some bounds when k equal to 3 that are very close to 1/3, which is what we would like. And so we get directly that the no isolated threshold is below this thing. So if your minimum degree is larger than this number, you don't have isolated matchings. This is what it's proved, just by plugging in this proof. And any progress that would be made on Caccetta-Häggkvist conjecture would directly imply a progress in our problem because of this equivalence I just showed you. For general graphs, though, it's not as nice. We have the implication just in one direction and not the other. I won't go into details, but we have only one direction. And so because of the Caccetta-Häggkvist conjecture, in the Caccetta-Häggkvist conjecture, the threshold is n over k, we believe that those thresholds should be at around n over k as well. For k equal to 2, though, this Caccetta-Häggkvist conjecture becomes much simpler. It's only about finding a graph that has no bidirected edge. So you want a graph that is directed but not, oriented, basically. Okay. And then you could plug directly this correspondence and get this n/2 bound. But you can also build the graphs by hand. They're not very complicated, and you get the same thing. And to prove the upper bound, you can also do some pigeonhole like proof, and everything works fine. So for k equal 2, you don't really have to use this correspondence. You can do everything by hand, and it works fine, and you get those nice bounds. Okay, I will slowly start going towards a conclusion. So one thing you can think of is, well, here if you think of the motivation we had initially, we're saying, oh, whenever you have a lot of perfect matchings, they should sort of start clustering together and start becoming close to one another. So another setting where you have a lot of perfect matchings is if your graph is balanced, bipartite, and regular. Okay, so if you add the regular condition, you always have a lot of perfect matchings. So if you look at the number of perfect matchings in log scale, for d-Dirac graph, you may have 0, and then all of a sudden you have a large number of them. For d-regular graph, it's always a lot of them. So if our intuition stands, then, well, this hk should have some nice property for some constant k for any d-regular graphs. Okay? And actually that's false. Okay, so the reason why is that for any fixed d, you can find d-regular graphs that have arbitrarily large girth. If they have arbitrarily large girth, the cycles are too long to do any switches on them. So everything is isolated in my space of perfect matchings. Okay, so I need to have some sort of relation between my degree and k to have something that works. I cannot have some independent constant. So what we show is that, well, when we're talking about regular graphs, the connected threshold, we have examples that are disconnected at 2n/k + 1. So it has to be bigger than this thing, but our proof of existence, they don't go from n/2 to this bound. So we have this very big window when k is at least 4, because for k equal 2 and 3, this matches the bounds we had. But for larger k's, we don't really know what's happening here. Okay? So I personally believe that this is the right answer, but so far the only thing we get is this n/2 bound upper bound. So open questions. So what happens for d-regular graph for larger k? That's the first question. And also the bounds we had for thawing and clustering, if you remember what the graph looked like, it was very non-regular, right? I had this small set of vertices with those cycles inside, and those didn't have the same degree as the other vertices. Same, like the three potatoes had very different degrees. So making this construction regular, we did not manage to do so. And so we don't have lower bounds for thawing and clustering for regular graphs. So that's also one direction. Then for Dirac graphs, as I said, when you're looking at two switches, we have a lower bound on the giant component threshold of n/2 plus constant, and we have connectedness at 2n/3. And we don't know what happens in the middle. So the giant component threshold is somewhere in the middle, and we have no idea where it is. And depending on the day you ask me this question, I would tell you either left or right. So I really don't know. And same thing, so, but this is probably a much harder question, localizing the no isolated threshold, and this is basically Caccetta-Häggkvist, so probably not the best problem to work on. Yeah. Okay. Another question we had when working on this, if you look at this drawing, you might wonder, well, is it true that you always have either lots of perfect matchings or no perfect matchings? We actually don't know of any construction that has just like a few perfect matchings. So it's not completely related to what we had, but we were not able to find anything inside this. We're either above this or at 0. And more generally, this type of question on taking some extremal problem and asking for the geometrical properties of this space of solutions, you can ask this for lots of extremal problems. Like Dirac is just an example. But for example, if you're looking at Dirac problems, instead of looking at perfect matchings, you could look at K-on factors, Hamiltonian cycles, or power of Hamiltonian cycles. All those examples are examples where we know that we have this supersaturation phenomenon. So after the threshold at which they start to exist, we start having lots of them. All those examples are also cases where we have this well-spreaded property above this threshold. So we know that we have lots of those structures inside, they're sort of everywhere, and we think that we should have the same type of phase transition for all those different structures. So that's our informal conjecture. We should have a sharp reconfiguration phase transition around the same threshold as the existing thresholds for all those different problems. And it would be nice to have some sort of way of attacking them, like a framework to attack them, maybe all at once. In other extremal problems, you don't have to look at Dirac problems, but actually for other extremal problems, some similar work have been done. So for example, for mental theorem, there's one paper on this reconfiguration transition for mental theorem. There's a series of papers for colorings of bounded degree graphs. And then there's a few other problems, but this is like, most of those results are like 1 or 2 years old. So this is like something that is starting. Okay, thanks a lot for your